In this section, we will learn about the fundamental theorem of calculus, which gives us a relationship between derivatives and integrals. So we'll start with what we call the evaluation theorem. And the evaluation theorem says if f is any antiderivative of a continuous function f, and we usually use a capital F for antiderivative and lowercase f for our function, on some interval ab, right? So to be an antiderivative means if I take a derivative of f prime, I would get f. Then the definite integral from a to b of the function f of x would equal to the antiderivative evaluated at the endpoints and then subtracted. So f of b minus f of a and then subtracted, right? So if, for example, I look at 2x, we know it's the derivative of x squared. So that means x squared is the antiderivative of 2x. So if I'm taking the definite integral from 3 to 5 of 2x, I can just take its antiderivative x squared, evaluate at 5, so 5 squared, evaluate it at 3, and I get 3 squared, and then subtract those two from each other. So 5 squared minus 3 squared, 25 minus 9 would give me 16, right? So in a way, if I know the antiderivative of the function, then I can simply evaluate the integral by subtracting the antiderivative evaluated at those 2 points, right? So next thing I'm going to do is define what it means to have an indefinite integral. So far, we've talked about an integral in a way as the area under a section of the graph, right? So an indefinite integral, so it's just an integral symbol, we don't have limits on it, is traditionally used as a notation for an antiderivative of the function, right? So if I say integral of f of x dx is equal to some function, that means that the derivative of my final answer is going to be the function I had inside the integral, the function we started with, right? So again, it's important to distinguish carefully between a definite integral and indefinite integral. In a definite integral, I always get a numerical answer, right? While in an indefinite integral, which is what we're looking at here, I get a function or a family of functions, right? So an antiderivative of a function is not always unique. It could have a constant associated with it. If I take a derivative of x squared plus 5 or x squared plus 7 or x squared plus 9, they all give me 2x. So when I find the antiderivative of 2x, I could have any of those functions as my answers. Could be x squared plus 5 or x squared plus 9. So we usually make that an x squared plus a constant. Then sometimes we can find that constant depending on what information I have about the function I'm finding the antiderivative for. All right, so next thing we'll look at is some integrals of functions that we know because we have studied their derivatives in the past. So to start with, we've taken a derivative of a power function, x to a power. And remember, when you take a derivative of x to a power, we subtract 1 from the power and multiply by the power we used to have. So the antiderivative of a function x to the n, I would do the opposite. So I increase the power by n plus 1 and then divide by that power, right? So if it's x cubed, I get x to the 4th over 4. Plus some constant. Again, I do need to allow for a possibility of there having been a constant when I took the derivative, a had disappeared. And again, that's true as long as n is not equal to -1, because if the power was -1, I would have a -1 plus 1, which is 0 on the bottom. And that also brings us to the formula when x is negative, when the power is -1, right? So if I had x to the -1, that's the same as having 1 over x. And we know that 1 over x is the derivative of a natural log function, right? And in this case, we have a natural log of an absolute value of x. because if x is negative, the natural logs cannot take on negative numbers, right? The domain of natural log does not include negative numbers, so we have an absolute value for the function, right? So x to a power, we have this formula for its antiderivative. If the power is -1, which means I have 1 over x, we have seen that that is the derivative of natural log. Right, so for e to the x, we know the derivative stays the same, therefore the antiderivative would stay the same. If I have any other number to the x, I get, again, that a to the x back, but I need to divide by natural log of a. And that has to do with how we took the derivative of a to the x. We got a to the x times natural log of a, so the antiderivative I would need to divide. We know the derivative of sine x is cosine x, so the antiderivative of cosine x, or the integral of cosine x, would be sine x. We know that the derivative of cotangent x is negative cosecant squared, so the integral of cosecant squared would be negative cotangent. We know that derivative of cosecant is negative cosecant cotangent, so the integral of cosecant cotangent is negative cosecant of x, right? And again, the formulas that we have here, e to the k to the x becoming e to the k to the x times 1 over k, because when we take the derivative, the chain rule would be applied, and we would have multiplied by k, so I need to divide by k in this case. The derivative of cosecant is the derivative of cosine is negative sine. Therefore, the integral of sine is negative cosine. Again, all of these have a constant added. Derivative of tangent would have been secant squared, so the integral of secant squared is tangent. And the derivative of secant is secant tangent. Therefore, the integral of secant tangent is secant. And finally, the derivative of tangent inverse was 1 over x squared plus 1. So the integral of 1 over x squared plus 1 is going to be tangent inverse of x plus the constant. Okay, and then we have a couple properties that also follow from how derivatives work. So if I'm integrating the sum of two functions, as long as they're continuous functions, I will be able to integrate the functions separately and add them. And again, we say these are integrable, right? So if an antiderivative can be found. And the integral of a constant times a function is the same as the integral of the function multiplied by the constant. And those follow from our derivative rules. Okay, let's take a look at an example. In this case, we want to find a general formula for an integral of the function 5x cubed plus 4e to the x. And again, remember the dx indicates that our independent variable is x. So we're going to take this integral with respect to x. Right, so first thing we're going to do is apply the last two rules we saw. We're going to break this integral up at the addition sign. So I have two smaller integrals, and I'm going to take the coefficients to the front and move it outside of the integral. So I have nicer looking functions to look at. So when it comes to integral of x cubed, we saw that when we take an integral of x to a power, we're going to add 1 to the power and divide by it. And when it comes to the integral of e to the x, we saw that it stays e to the x. The derivative of e to the x stays the same. Therefore, the integral stays the same. So what we are going to end up with is 5 multiplied by x to the 4th, the 3 plus 1, divided by 4, plus 4 times e to the x, plus a constant of integration. So remember, again, there could have been a number here, any constant. When we took the derivative, it had gone away. So we should allow for there to be a constant when we find an indefinite integral. And the last thing we're going to do in this case is combine the 5 and x to the 4th over 4 into one fraction and get 5x to the 4th over 4 plus 4e to the x plus a constant. Now, so far in this video, we've seen the evaluation theorem, defined what an indefinite integral is, and seen some of the properties. Next, we want to start talking about the fundamental theorem of calculus, but first we need to define a function, a new function, in terms of integrals. So we're defining the function g of x to be the integral from a to a number x of a function f of t dt. So here's a graph of f of t. This is the blue graph. So I'm integrating it. Instead of going a to b, which would give me the entire area, I'm going from a to some number x between a and b. And depending what x is, this area will change. And I get a function that is dependent of the value of x, right? So it starts from a, but the area only goes up to the different values of x that I may want to use. And that's how we define our function. So just so we understand what that means, let's look at a demonstration here. So here we have a graph of a function. F of x is 3 minus x over 2. And that would be the blue line that you see. And then in a second, we're going to see what happens to this other function that we have. This is kind of plays the role of our g of x. It says capital F. We'll see why in a few minutes. But this plays the role of our g of x. It's defined as the integral from 0. And here are the starting point I'm going to work with is 0, all the way to different values of x of this function. And we use f of t, d of t, so we don't have two sets of x's here, right? So as I increase the value of x, we'll see the area, and also a second function will appear. The graph of a second function appear, right? And that red graph is the graph of what we looked at, we call g of x, or in this case, capital F of x. And notice as I move to the right, the area keeps getting bigger and that graph keeps going up. So that's the function we had defined. And in this example that I'm looking at some point, my function is going to go below the x-axis right here. And notice then when we talk about net area, what's below the x-axis gets subtracted, and g of x keeps getting smaller and smaller. And as you notice, I start with a linear function, and this graph turned out to be a parabola. So that's the function that we had defined in our slides, and what we're going to use to talk about the fundamental theorem of calculus. Right, so now that we've looked at this function, this is what the fundamental theorem of calculus part 1 says. So if f is continuous on some interval ab, then the function we just defined, g of x equals the integral from a to the x of f of t dt, where x is some number between a and b, is the antiderivative of f. And that means if I take a derivative of g prime of x, I get my function f of x. And this, again, establishes a relationship between integrals and derivatives, right? So if I take an integral, in this case, so remember integrals were defined as an area, I, in a way, am dealing with the derivative of a function. Right? So if I then put this together with the first theorem that we saw, we get the entire statement of the fundamental theorem of calculus. Right? So here's the full statement. Suppose f is continuous on AB. If g of x is the integral from a to x of f of t dt, for any x between the values a and b, then g prime of x is f of x, right? So the derivative of an integral from a to x gives me the function that I had inside of the integral. And then part 2 goes back to the initial theorem that we saw. And if I have a definite integral of a function, I can just evaluate the antiderivatives at the two endpoints of the interval. So these two things, again, put together, establish a back and forth relationship between an integral and the derivative. And that's what we call the fundamental theorem of calculus.